So ionic compounds have crystal structure. They form so that oppositely charged ions are as close together as possible. This 3D array, this 3D array of alternating positive and negative ions is called a crystal lattice. So when you think about lattice, like or kind of like fence lattice, you know, the cheating way to make a fence, that's kind of what it's like, right? It's like a crystal in that lattice type of formation, a lot of patterning, and it's actually, it makes it stronger. Okay. So these are some examples of like kind of what a crystal lattice would look like. Since all the attractive forces in the lattice are the same, you cannot call them molecules. Each positive ion is attracted to all of the negatives around it, and vice versa. So it's not like the one sodium ion is specifically attracted to one chlorine ion. It kind of has an attraction to all of the negative ions and all the positive ions. So the chemical formula is the lowest whole number ratio, just like normal ionic compounds, like because it's an ionic compound. But so sodium chloride would have a crystal lattice structure like that, kind of like form a cube-like. Were you good? Or no? It's good? Okay. There are many different crystal shapes, and they depend on the way, the different crystal shapes, and they depend on the way the ions will pack together. Shape also depends on the relative size of the ions and the charges on the ions. Okay, so next we're going to talk about metallic bonding. Now, I want you to just think about this for a minute. When we think about something like conductors or insulators, what are metals? Conductors. Okay. What is electricity? It's a flow of electrons. Okay. So, and we think about, okay, we need like things like copper wire. You know, that's a really good conductor to use to transport electricity, right? Okay. So, metals allow for the flow of electrons. You see that? Metals are conductors. We know that conductors allow for the flow of electricity, which is the flow of electrons. So there's something about metals that allows for the electrons to move freely. Okay? That's really important. And in developing this theory of a metallic bond. So metals allow what to move freely? Electrons, okay? So metallic bonds must also allow what to move freely? Electrons. So we need some sort of a bond theory where electrons are free to move. And this theory, we say that it's like a sea of electrons, okay? So it's like the water or something is a bunch of electrons, and the rest of the atom is just kind of floating in this sea of electrons. Because they're allowed to flow, right? Think about it like water. Okay, so it's like the electrons need to be allowed to flow. So, with your notes then, most metals are solid at room temperature, which means that there must be strong attractive forces holding them together. Because if you think about it, boiling point or melting point needs to be really high for metals, right? We know that if we're going to melt a metal, it needs to be really high. High melting point, high boiling point means strong bonds. Yes? Yeah? Okay. So, metals do not form covalent or ionic bonds with other metal atoms. So they're special. In metallic bonding, all the atoms share valence electrons. In metallic bonding, all the atoms share all the valence electrons. So what we say then is that the valence electrons are delocalized. Delocalized, which means they are free to move from one atom to another. So this frees up the electrons. They're like the traveling nomads. They're not, you know, anywhere specific. They're not locals. You know, they're just travelers. They travel around from town to town doing whatever they want. Okay? So they don't have to be with a specific atom anymore. They get to kind of wander around, okay? So this is kind of crazy, don't you think? These electrons, they're just free willing it, you know, whatever they want to do. Okay, metallic bonds are made up of a network of positive metal ions, in a sea of electrons, like water. Or ocean of electrons, if you prefer, or river, or stream, or pond, or lake, or pool. Whatever visual you would like. So, a metallic bond, then this is a definition, is the electrostatic force of attraction between the positive metal ions, between the positive metal ions and the negative C of electrons. So this is like the key kind of our definition that would be important to memorize, okay? This is kind of our summary explaining metals. And I was saying before, this theory helps to explain the properties of metals. So for example, they're good conductors of electricity, which we said, you know, electricity is the flow of electrons. They can conduct heat. They're ductile, meaning like we can stretch them out into a wire, and they're malleable. So this is just something kind of special about our metallic bond. So yeah, and you have this picture here. Do you have it labeled? No, I want you to label it actually. So here, where on the left side, where the arrow is pointing like all to the middle, so those are the metal cations, or the positive atoms. Okay. And then on the right side, those arrows are kind of all pointing to the middle where there's electrons just floating around. And that's the sea of delocalized electrons. So those are our metals. Okay, and now we're just going to talk about a couple properties of solids and mostly just talk about our conductivity as we've been talking about so far. So, the mechanical properties of solids are determined by the types of bonds in the substance. These delocalized electrons causes the bonds to be non-directional. Which allows it to be malleable and ductile. So those bonds aren't in a specific direction, and so you can bend the object a lot more than, say, thinking about bending a crystal, right? Crystals aren't very bendy, you know? Thinking about bending a diamond. It doesn't work. Solids that do not have delocalized electrons have directional bonds, which causes them to be brittle and hard, so like our ionic compounds.